So the last thing I want to mention is just the fact that gradient vector fields show up in all sorts of different places in applications is related to a couple different things. One of them is that because the gradient field of a scalar function always points uphill, like as quickly uphill as possible on the graph of that function, if I follow the gradient vector field of a scalar valued function, I'm always going to be going uphill on the graph. And so, as you might imagine, if I keep following it long enough, I'm probably going to reach the top of some hill somewhere, right? And so gradients give us a way of numerically finding local maximum points. All we have to do is follow the integral curves of the gradient, and eventually they're going to lead us somewhere that's the top of some hill. We can also find the bottoms of valleys if we just walk in the opposite direction of the gradients, right? Because that always points me downhill. So if I follow the opposite of the gradient, I'm going to be going all the way downhill and finding the local minima of a function. That method, when you implement it as a numerical approximation, is called the method of gradient descent. And so it's the most common way of, if we have a really complicated function, we want to find out where its maximum and minimum points, we can just start at any old point and either follow the gradient uphill or follow the opposite of the gradient downhill until we find a local maximum or local minimum point. So that's a really nifty thing. It also shows up a lot in physical science applications because there are a lot of places, a lot of systems that are called conservative systems in physics. And a conservative system is the one that always seeks to minimize its total energy. And so it does that by sort of following the easiest path from a higher point on the potential energy surface to a lower point on the potential energy surface. And so one particular example of where that happens is in meteorology. I've had this lifelong dream. I've always wanted to be a weather person on TV, right? That gets up in front of a weather map and points at it on TV and talks about weather. So this is about as close as I'm ever going to get to doing that as a career. But you used to see these maps a lot on meteorology on the local news. They've kind of fallen out of favor in the past handful of years. But what it's showing us is sort of these cold fronts and warm fronts that kind of mark where the masses of cold air moving, where masses of warm air moving. But rather than those, what I want to draw our attention to are these blue curves that are being drawn on here. These curves are contours, and they're contours of the barometric pressure function. So at each point on this map, this is a map from 9:30 this morning, I think. Yeah, 9:45 Eastern. So this was from this morning. We have actually really pleasant weather here in Massachusetts today. So over here-ish. Oops, sorry, look at my pen tool. So you are here approximately. Anyway, these blue lines are lines of constant barometric pressure. And so over here where we have a big red capital L, it's marked with a 994. That is the local minimum of the barometric pressure function. So we call that a center of low pressure on this map. 994 millibars would be the pressure at this place. And then as we count outwards, it's 996 millibar contour right here, and then a 1000 millibar contour next, and then 1004, 1008, and so on and so on. And eventually, if we get into northern Quebec, sort of the border with Newfoundland over here, we have a high pressure center, right, at 1015 millibars. And so we're seeing a contour plot of the barometric pressure function on this map. And why is that important? What does that tell us about the weather? Well, if I have an area of high pressure air over here in Quebec and an area of low pressure air over here at the tip of Greenland, what's going to happen is that the air wants to move from high pressure areas to low pressure areas, right? If I increase the pressure over here, it's going to make that air want to move and distribute that pressure out and minimize the energy. So it moves along the opposite of the gradient of the pressure function. And so what that tells us is it tells us how the wind is blowing from these isobars, because the wind is nothing more than the movement of air from a high pressure region into a low pressure region. And so, like any good gradient, the wind is going to blow, the air is going to move here in the direction which is, again, it's the opposite of the gradient, so it's going to move in the direction of the greatest decrease of the barometric pressure function. And so it'll be perpendicular to these contours. And where the contours are close together, the wind is going to be blowing pretty rapidly. So these areas up here over the North Atlantic, pointing up towards Greenland, probably pretty strong winds. Whereas where the contours are spaced pretty far apart, like, I don't know, maybe up here in Hudson Bay or something, then the wind is going to be not quite as strong because the contours are a little bit further apart over in there. And so this is one of those great applications where, 10 years ago, when these maps were all over the local news, multivariable calculus students could sort of immediately connect with, oh yeah, barometric pressure and wind. That's an obvious place where we see gradient vector fields and contour plots in our everyday life. But since these have kind of disappeared from most local weather broadcasts, and people honestly don't watch that much local weather news broadcasts anymore, especially people of the age of the traditional college student, we've sort of run out of this as a cultural touchstone. But I still like it a lot, both because of my secret dream to be a meteorologist on TV, and also because it's just a great applied example that once you sort of see how it works, it's like, oh, obvious about how this should work. So if I want to find the areas of low pressure, I'll just follow the wind, right? And if I follow the wind, it will lead me down to this low pressure area in the north of Greenland, or possibly the one over here on the right-hand side of the map over in Spain, sort of depending on where I start. If I follow the winds, it could take me to either of those two places. And if I go the opposite direction of the wind, I'll end up at one of these high pressure centers. So it's a pretty calm day in the northern hemisphere today. I wish we had like hurricanes or something to make this more interesting, but yeah, we'll make do with what we've got.